Root locus means locus of roots, locus of roots of closed loop system as k varies from 0 to infinity, as k varies from 0 to infinity. That is called the locus of roots. Up to second order, up to second order, we can easily find the roots and we can draw. But that too, we have to find the infinite number of roots. Then only we can draw. So some techniques are there, shortcut methods are there to draw the root locus without finding roots. There are some 8 set of rules. By using that, we can find the root locus. Let us see all those rules. All those rules. Set of rules. Before that, we have to find that closed loop transfer function. What is that? G of s upon 1 plus g of s h of s. So what is root locus? Roots of this denominator as k varies from 0 to infinity. That is called the characteristic equation. 1 plus g of s h of s equal to 0. That is the characteristic equation. The roots of this characteristic equation as k varies from 0 to infinity are called root locus. So this can also be written as g of s h of s can be written as 1 plus p of s equal to 0, or p of s equal to minus 1. P of s is g of s h of s, loop transfer function. Or we can say that modulus of p of s equal to 1 and angle of p of s. So we can separate this minus 1 in two parts. One is magnitude, another one is angle. Minus 1 means 180 degree. Therefore, angle of p of s equal to 180 degree. Normally we won't say 180 degree. Odd multiple of 180 degree. Odd multiple of 180 degree. That's why we can say that 2q plus 1 multiplied by 180 degree. Plus 180 minus 180 both are same. That's why we can say that plus or minus 2q plus 1 multiplied by 180 degree. So this minus 1 can be separated into two equations. One is called modulus of p of s equal to 1, or modulus of g of s h of s equal to 1. That is magnitude criterion. That is called magnitude criterion. Another one is called angle of g of s h of s equal to 180 degree. That is odd multiple of 180 degree. 2q plus 1, where q equal to 0, 1, 2, 3, etc. So this can be said as plus or minus 2q plus 1, 180 degree, angle of q of s. As k varied from 0 to infinity, always this condition will be satisfied for at least 1k. First condition always will be satisfied. If you substitute some value of k, as it varies from 0 to infinity, for any one of value, this condition will be automatically satisfied. That's why we can ignore this condition, because always it is satisfied for one value of k or another value of k. Therefore, any point that satisfies this condition is a roots of denominator polynomial. Any point that satisfies, suppose I am having a point s equal to p1. If you substitute p1 is a pole, if you substitute in this angle criterion, if it gives odd multiple of 180 degree, then point p1 is on the root locus. Similarly, we can check for p2, p3, etc. Like that, we can check any point. If it satisfies this, this will automatically be satisfied, because k varies from 0 to infinity. For one value of k or another value of k, this point will be satisfied. So we have to draw the root locus for second condition only, second equation only. So this second criterion is called angle criterion. Angle criterion. Suppose I am having some poles. Here one pole, another pole here, another pole here. 1, 0 is here. So what is the angle of, suppose I want to check whether this point P1 is on the root locus or not. For that, what I have to do is, I have to find the angle criterion, angle of G of S, H of S. What is that angle of P of S, H of S? Line connecting this pole and P1. What is the angle? Theta 1. What is the angle of this P1, this second pole? First pole, second pole. What is the angle? Let it be theta 2. What is the angle? Theta 3. What is the angle of with 0? Theta 4. If you add theta 1, theta 2, theta 3 and theta 4, if the angle, total angle is odd multiple of 180 means that point will be on the root locus. So we have to add minus theta 1 because pole is in the denominator. Pole is in the denominator. If you write G of S equal to S plus 1 upon S plus 2, S plus 3 means these are all in the denominator. If you find an angle for this, it will be negative. If you angle for 0, it will be positive. Therefore, theta 1 is negative because pole. Theta 2 is negative because pole. Theta 3 also negative because pole. Theta 4 is for 0, that's why positive. If you add theta 1, theta 2, theta 3, theta 4, if it is equal to odd multiple of 180 degree, then this point P1 is on the root locus. It's not possible to find this way. We have to check every point whether it is on the root locus or not. If you check like that, it's not possible to check. So there are set of rules which satisfies the second condition. 8 rules are there. That rules we will see. By using that, we can find the root locus. The first rule is root locus is symmetrical about real axis because if the roots are on the real axis, suppose I am having some 3 poles on the real axis, 1 pole, 2 poles on the complex, then it will be like this. Another 0 is there, that is also on the real axis. 1 more 0, 2 more zeros are there, that is complex, that's why it will be like this. If you see, when k equal to 0, only open loop poles are there. Already we know that k n of s upon k multiplied by numerator of s plus denominator of s. This is closed loop transfer function T of s. If you put k equal to 0 in the denominator, only denominator of s, only there. That is open loop transfer function. When k equal to 0, closed loop transfer function becomes open loop transfer function. Closed loop transfer function becomes open loop transfer function when k equal to 0. Therefore, the poles and zeros are for open loop only. So if you draw the open loop poles, it will be like this. So these are all on the root locus because when k equal to 0, it starts here, it starts here, it starts here, it starts here. If you see that above real axis, the below real axis, if you see, it is mirror image of whatever in the top part. So this is mirror image of top part, or the top part is mirror image of bottom part. It will be like that. Therefore, we can say that this root locus is symmetrical about real axis. How many branches will be there? Here, when k equal to 0, here the P1 pole starts here. When k equal to 0, P2 pole starts here. When k equal to 0, P3 pole starts here. When k equal to 0, P3 starts here. When k equal to 0, P4, P5 starts here. If we increase k, this pole will move. This pole will move. This pole also will move. This pole also will move. This also will move. This also will move. This also will move. So it is moving. So the number of branches, number of root locus branches equal to number of open loop poles. So here, how many open loop poles? 5 open loop poles. Therefore, 5 root locus branches are there. Root locus branches are there. Second condition is the root locus are symmetrical about real axis. Symmetrical about real axis. So that is the first condition. First rule. All, how many root locus branches? Number of open loop holes. Number of open loop holes. That is first rule. Second rule, all branches of root locus starts at open loop holes. All root locus branches starts at open loop hole. That we will see now. T of S equal to what? T of S equal to K multiplied by S power M plus A S power M, A1 S power M, A2 S power M minus 1 plus etc. plus A0. Numerator polynomial of degree M. Denominator polynomial will be B1 S power N plus B2 S power AM M minus 1, AM minus 1, let us call like that. Bn minus 1, etc. plus etc. So B0, up to B0 it will come. So what is the order of the system? Order is N. How many poles for this? N number of poles. How many root locus branches? N number of root locus branches. But where it will start when k equal to 0, that we have to say. For that, we can say that this is G of S. Let us call G of S. Factorize this. How many poles you will get? Z1, S plus Z2, etc. S plus Zm. Because M, degree of numerator is M. Degree of denominator is N. Therefore, S plus P1, S plus P2, etc. S plus Pn. N number of poles. So you'll get like this. The closed loop transfer function can be factorized like this. It can be written as K multiplied by product of J equal to or I equal to 1 to M product of S plus Zi. Like that. This Z1, Z2, Zm, the zeros can be like this product of. The denominator can be written as J equal to 1 to N S plus Pj. Like that we can write. We know that for a unity feedback system H of S equal to 1. Therefore, this 1 plus G of S H of S can be written as sum of numerator polynomial plus denominator polynomial. That characteristic polynomial is 1 plus G of S H of S. That is K. That is the product of I equal to 1 to M S plus Zi upon product of J equal to 1 to N S plus Pi equal to 0. This is the characteristic polynomial. This is the characteristic polynomial. Or we can say that product of J equal to 1 to N S plus Pi plus K times product of I equal to 1 to M S plus Zi. This is J, no? This is J. Equal to 0. If you put K equal to 0, this part becomes 0. This part becomes 0. When K equal to 0, the characteristic polynomial becomes this denominator part only. Denominator part only. Therefore, root locus branches starts at open loop holes when K equal to 0. When K equal to 0. This can also be written as what we got finally, product of J equal to 1 to N S plus Pj plus K times product of I equal to 1 to M S plus Zi equal to 0. If we divide on both sides by K, what you will get? 1 by K product of J equal to 1 to N S plus Pj plus this becomes 1. Therefore, product of I equal to 1 to m s plus zi equal to 0, dividing on both sides by k. If k tends to infinity, what will happen? K tends to infinity, this part becomes 0. This part becomes 0. This part becomes 0. This part alone is there. Therefore, when k equal to 0, it ends at 0. It ends at 0. We can say that the root locus branches are starts at pi's, pj's, starts at pj's and ends at zi's. Like that we can say. Because when k equal to infinity, this part becomes 0. This part alone is there. Therefore, root locus branches will end at open loop zeros. Open loop zeros. Starts at open loop poles. That we know. But we know that m is always less than n. N is degree of denominator polynomial. M is degree of numerator polynomial. Therefore, the remaining, how many root locus branch will not end at 0? N minus m branches. Only m branches will end at 0. N minus m branches will, where to end? Where it will end? Where it will end? N minus m branches. Because out of n branches starts at open loop poles. How many poles will be there? Open loop poles, n poles will be there. It starts at n poles, end at m zeros. The remaining pole root locus branches are n minus m branches. Where it will end? It will end at infinity. It will end at infinity. So n minus m branches, n minus m branches, n minus m branches will end at infinity. Will end at infinity. For that, what we can do is, what is the characteristic polynomial? 1 plus product of j equal to 1 to m s plus zj. I put I earlier, so now also I put I. Divided by product of j equal to 1 to n s plus pj equal to 0. Or I can say that product of I equal to 1 to m s plus zi upon product of j equal to 1 to n s plus pj equal to minus 1. Already here k is there, in the numerator k is there. If you bring that k in the right hand side, you will get 1 by k. When k tends to infinity, it becomes 0. Here, the numerator has only m poles, number of terms. This number of terms equal to m. Here, this number of terms equal to n. We know that m is less than n. Therefore, as a limiting case, to this becomes 0, this s should be tends to infinity. This s tends to infinity e power j theta. If s tends to infinity, then only the left hand side becomes 0. Already, as k tends to infinity, right hand side is 0. When left hand side will be 0? As s tends to infinity. Therefore, the remaining poles n minus m branches will end at infinity. N minus m branches will end at infinity. So that is second rule. What is the second rule says? Second rule says all branches of root locus start at open loop poles when k equal to 0. Suppose I am having an open loop transfer function. G of s equal to k s plus 1 upon s plus 2, s plus 3, s plus 4. This is open loop transfer function. When k equal to 0, it will start at open loop pole. Open loop pole means where it will start. Where are the poles? One pole is at minus 2, another pole is at minus 3, another pole is at minus 4. Here and all, the root locus branch will start. 1 0 is there. Where? Here at minus 1, 1 0 is there. One of the branches will end here. So it may be like this. This 2 starts here and end at -1. One branch will end at -1. Remaining 3 branches will go to infinity. How many? How many? Totally how many branches? Only 3 branches. One end at -1. The remaining 2 will go to infinity. So I know this by rule. I know this root locus. They will meet each other at some point. Then it will go up. Another one will go down. Huh? Third rule says a point on the real axis. A point on the real axis lies on the root locus. Lies on the root locus. What is point on the real axis? Point on the real axis. This is S plane. We will draw the root locus on S plane. This is real axis. This is imaginary axis. Any point on the real axis. Suppose I am selecting a point S naught. A point. This is a point on the real axis. On the root locus, if the sum of poles and zeros on the real axis to the right of the point is odd number, we will take the same example. What is that? We took S plus 1 upon S plus 2, S plus 3, S plus 4. So here minus, this is 0. This is 0. The remaining, this is minus 2, this is minus 3, this is minus 4. This is minus 1. 1 0 is at minus 1. Other 3 poles are at minus 2, minus 3, minus 4. So one point I am selecting here. Whether this point is on the root locus or not, how to check? We know that line joining from all poles to that point. Already we have seen Evans condition. Suppose this point, whether this point is on the root locus or not, how we will find? We will draw a line from that point to all poles and zeros. We will measure the angles theta 1, theta 2, theta 3. If we add all the angles, it should be odd multiple of 180 degree. So this is the point. So draw a line from all poles and zeros. From minus 1 to S naught, if you draw a line, the angle of this line is 180 degree. Minus 180 degree. If you draw a line from minus 2 to this point S naught, the angle is 0 degree. Angle is 0 degree. Towards the right we are. Any point is there. If you draw a line like this, what is the angle? 0. A point is there. If you draw a line like this, what is the angle? 180 degree. Therefore, this is 0 degree. What is the line joining minus 3 and the S naught? That is also 0 degree. What is the line joining minus 4 and S naught? That is also 0 degree. Add all the angles. If it is S naught, from S naught, if you add S naught to 0 means positive. Plus 1, plus, because it is in the numerator. Plus 180, plus 180, angle is minus 180, but plus minus 180, plus 0, plus 0, plus 0 equal to plus 180 degree. Sorry, minus 180 degree you are getting. Because the angle is minus 180 degree. If you add all the angles, you will get minus 180 degree. It satisfies the condition. Therefore, S naught is on the root locus. If you select any point between minus 1 and minus 2, angle will be 180 degree. Am I correct or not? Angle will be 180 degree. Therefore, all points between minus 2 and 1 are root locus. I have drawn the root locus. Root locus starts at minus 2 because minus 2 is open loop pole. Starts at minus 2, ends at minus 1, open loop 0. So, any point between minus 2 and minus 1 is root locus. Therefore, one branch completed. One branch completed. It starts at minus 2, ends at minus 1. Similarly, we have to check here. I am selecting S1, another point between minus 2 and minus 3. Whether it is on the root locus or not, I have to check. Draw angle from minus 1 to S1. 180 degree, minus 180 degree. From minus 2 to S1, you will get another minus 180 degree. Another minus 180 degree. From minus 3 to S1, you will get 0. Minus 4 to S1, you will get 0. So now we have to add. This is for pole. This is for 0. That's why we have to put plus, we have to add. But we have to subtract this. We have to subtract this. Why? It is angle for pole, denominator. That's why minus. Minus of minus, this becomes plus. This is minus. Therefore, net angle becomes 0, not 180 degree. Not 180 degree. That's why any point between minus 2 and minus 3 is not on the root locus. Any point between minus 2 and minus 3 is not on the root locus. Suppose let us select one more point, S2. S2 is a point, test point. I am selecting test point to check whether it is on the root locus or not. Between minus 3 and minus 4. How many angles? If you draw a line from minus 1 to S2, minus 180 degree. If you draw a line from minus 2 to S2, another 180 degree. If you draw a line from minus 3 to S2, you will get another 180 degree. Draw a line from minus 4 to S2, you will get 0. What are all for poles? This is for poles. This is also for pole. This is for 0, therefore minus. This is plus, minus, minus. Minus or minus, this becomes plus. This also becomes plus. These two getting cancelled. This is minus 180, this is plus 180, these two getting cancelled. What is the remaining angle? Plus 180 degree. Plus 180 degree. Therefore, it is odd multiple of 180 degree. Odd multiple of 180 degree. Therefore, any point between minus 3 and minus 4 is on the root locus. Therefore, 4 starts. Always we said 4 is open loop only starting point. Therefore, minus 4 also starting point. Minus 3 also starting point. Therefore, if minus from minus 4 starting point, minus 3 also starting point, that's why they will come and meet at one point. They will come and meet at one point. Let us select one more test point after minus 4. That is S3. After minus 4, all poles and zeros on the right hand side. All the poles and zeros are on the right hand side. What is the angle from minus 4? Minus 180 degree. What is the angle from minus 3? Minus 180 degree. What is the angle from minus 2? Minus 180 degree. What is the angle from minus 1? Minus 180 degree. These are all in the denominator. First 3 are in the denominator. That's why minus. It becomes plus, plus, plus. This is minus. These two getting cancelled. What is the remaining? 180 plus 180. 360. It is not odd multiple of 180 degree. It is not odd multiple of 180. It is even multiple of 180. 360 degree is 0. 360 degree is 0. Therefore, it is not odd multiple of 180 degree. Therefore, any point from minus 4 to infinity, minus infinity, it is not on the root locus. It is not on the root locus. That's all. So, these two branches approach each other and break away at this point. One goes to plus 90, another goes to minus 90. That we will see in another rule. So, whether it is on the root locus or not, we check. Real axis, whether it is on the root locus or not, we check. That is third rule. Fourth rule, by using 3 rules, we can draw some root locus. Let us draw the root locus for this. Draw the root locus for the unity feedback system with open loop transfer function. Zeros are what? How many branches? How many poles? How many poles? N equal to 3. How many zeros? 2. How many zeros are? Z equal to minus 1 comma minus 3. Am I correct or not? Poles are equal to what? 0 comma minus 2 comma minus 4. Am I correct or not? These are all poles. Therefore, n equal to 3, m equal to 2. How many root locus branches are there? Number of root locus branches equal to number of open loop poles. Therefore, number of branches equal to 3. How many will end at 0? 2 branches. 2 branches will end at 0 because 2 zeros are there. 2 branches end at zeros because 2 zeros are there. How many will go to infinity? Only one will go to infinity. Only one, because one goes to infinity, because n minus m equal to 3 minus 2 equal to 1. N minus m branches will end at infinity. Now we have to draw the root locus. So we have to take S plane. What is the first rule says? Number of root locus branches equal to number of poles. Root locus branches are symmetrical about real axis. This is the first condition. What is the second condition? Root locus branches starts at open loop 0. Here 1 0. Minus 2 another 0. Minus 4 another see, one pole is at 0, another pole is at minus 2, another pole is at minus 4. Parent all 0. 0 is at minus 1. Minus 1. Another 0 is at minus 3. That's all. Now we have to apply third rule. Third rule says what? Open loop pole, second rule says root locus branches starts at open loop poles. So this is one starting point. This is another starting point. This minus 4 is another starting point. Ends at where it will end. One root locus branch will end at minus 1. Another will end at minus 3. Third will end at infinity. Third will end at infinity. 3 root locus branches are there, out of which one will end at infinity. We have to check, take the test point and check whether it is on the root locus or not. If we select between 0 and minus 1, any point between 0 and minus 1, if I select one point to its right, how many poles and zeros? Odd number of poles and zeros. Therefore, it is part of root locus. By using third rule, we can say that if you select any point between minus 1, 0, it is part of root locus. Therefore, this root locus branch start at 0, end at minus 1. One branch is over. Between minus 1 and minus 2, no, it is not part of root locus. Why? Any test point if we select, therefore I am selecting test point between minus 1 and minus 2. I am selecting test point between, S1 is this test point, between minus 1 and minus 2. To its right, how many poles and zeros? Even number of poles and zeros. Even number of poles and zeros. Therefore, it is not part of root locus. Real axis is not part of root locus. If we select between minus 3 and minus 4, to its right, how many poles and zeros? Odd number of poles and zeros. So you will get 180 degree. Therefore, this any point, any test point between minus 3 and minus 2 is part of root locus. Therefore, it starts at minus 2, end at minus 3. Starts at minus 2, end at minus 3. That is also root locus. Second branch also over. If we select any point between minus 3 and minus 4, it is not part of root locus. To its right, how many poles and zeros? Even number of poles and zeros. That's why it is not part of root locus. After 4, if you select, after minus 4, if you select any point, to its right, odd number of poles and zeros. Therefore, from minus 4 up to infinity, it is part of root locus. So, all the 3 root locus branches we have drawn. Completed. So, root locus sum will be asked in 8 marks as well as 2 marks. This sum is 2 marks. You can draw the rough root locus branch. Rough root locus branch. So, one root locus branch starts at minus 0, another starts at minus 2, third starts at minus 4. The root locus starts at minus 0, ends at minus 1. Minus 2 ends at minus 3. Minus 4 ends at infinity. That's all. That's all. Fourth rule. Fourth rule. We have seen that n minus m branches will end at infinity because number of poles n number of poles, m number of zeros. N poles, the root locus branch will at n points. So number of branches equal to n. Only m poles will end at 0. The remaining n minus m branches will end at infinity. End at infinity. In the previous case, this root locus branch end at infinity at an angle 180 degree. It goes to infinity at an angle 180 degree. So, like that, here we have to find an angle for n minus m branches Suppose let us assume that n minus m branches are end at infinity. Some root locus branches end at infinity. Here one pole, here one pole, here one pole, here one pole. Here one end, one ends. Here one ends. This is at infinity. S1 is at infinity. S2 is also at infinity. The root locus branches starts here. Root locus branches starts here, approach each other, and it will go to S2, infinity. So, if you draw a line parallel to this line, that is called asymptote, because this parallel line will meet the graph at infinity. That is why it is called infinity. Infinity means, asymptote means tangent at infinity. Tangent, two parallel lines, mathematically where they will meet? Two parallel lines where they will meet? At infinity. Mathematically they will meet at infinity. Therefore, a parallel line is called asymptote. Asymptote means tangent at infinity. Tangent means what? They are touching each other. Where they are touching? At infinity. Therefore, if you draw a asymptote parallel to this graph, if you draw an asymptote, this is called asymptote. 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 This asymptote will meet the graph at infinity. Another goes to infinity at this angle. If you draw a line parallel to this, this is called another asymptote. This is called another asymptote. What is the angle of that asymptote? We can find the angle of asymptote. So, how many branches end at infinity? N minus m branches. N minus m branches end at infinity. N minus m branches end at infinity. What is the angle made by all these asymptotes? Let us assume that it is called phi a. What is the angle contributed by this S1 and S2? Phi a. Angle contributed by S1 and S2 are phi a. Because it is a point at infinity, if you draw a line from that point to each pole, the angle is phi a. The angle is phi a. That is called asymptote. That is called asymptote. What is the total angle made by all these points? N minus m multiplied by phi a. Am I correct or not? Each giving an angle of phi a, the total angle. How many points at infinity? N minus m points at infinity. So n minus m branches end at infinity. Therefore, angle made by all these points, I am having n minus m points, S1, S2, S3, etc. N minus m branches points at infinity. If we draw a line from that infinity to that pole, that angle is phi a. Therefore, total angle made by all these lines equal to n minus m multiplied by phi a. That must be equal to 2q plus 1 multiplied by 180. Am I correct or not? Because that is the criteria to satisfy whether that point is on the root locus or not. So if you add all these angles, you will get 2q plus 1. Therefore, that angle phi a equal to 2q plus 1 multiplied by 180 divided by n minus m, plus or minus 2q plus 1 plus or minus we can add, plus or minus 2q plus 1 180 divided by n minus m. As q varies from 0, 1, 2, etc. One phi a you will get for 0, another phi a you will get for 1, another phi a you will get for 2. Like that, you will get n minus m angles. N minus m angles you will get. So, whether this point is on the root locus or not, for that what we have to do? From S1 to all poles we have to draw line. That is called asymptote. The angle made by S1 to all poles equal to phi a. How many lines we have drawn? N minus m lines we have drawn. Because the remaining are ended at 0. Only n minus m lines we have drawn. Therefore, total angle equal to n minus m multiplied by phi a. N minus m multiplied by phi a. Therefore, the angle of asymptote equal to plus or minus 2q plus 1 multiplied by 180 divided by n minus m. That is the formula to find the angle. These asymptotes are meeting at sigma a. This is one asymptote. This is another asymptote. This is third asymptote. This is fourth asymptote. This is fifth asymptote. All will meet at a point called sigma A. Sigma A. All will meet at a point called sigma A. That sigma A equal to sum of real parts of poles minus sum of real parts of zeros divided by n minus m. That is equal to sum of real parts of poles minus sum of real parts of zeros divided by n minus m. That is the formula. That is the formula. Sigma A equal to, what is numerator polynomial? K multiplied by product of I equal to 1 to m s plus z I divided by product of 1 plus characteristic polynomial j equal to 1 to n s plus p j equal to 0. Equal to 0, or we can write k multiplied by product of I equal to 1 to m s plus okay. This can also be, the numerator can also be written as s power m plus sum of I equal to 1 to m zi of s power m minus 1 plus etc. plus product of I equal to 1 to m s power, that is z all zi's. If you expand this, you will get the polynomial like this. What is this? The first term is s power m, second term is s power m minus 1, the last term is s power 0. The coefficient of second term is sum of all zeros. Sum of all zeros. The coefficient of last term, constant term, is product of all zeros. Similarly, denominator also we can write like that. S power n plus sum of poles s power n minus 1 plus etc. The last term is product of all poles. This way we can write. That is equal to minus 1. That is equal to minus 1. This can, if you divide the denominator by numerator, divide the numerator polynomial by, divide the denominator polynomial by numerator polynomial, divide the numerator and denominator by numerator polynomial. What you will get? Numerator becomes 1. Denominator becomes s power n minus m plus sigma I equal to 1 to n minus pi's minus sigma j equal to 1 to m, j equal to 1 to m, zj s power n minus m minus 1 plus etc. plus the product of these two terms you will get. Let it be. For large value of s, we can approximate the denominator to only two terms. Only two terms. For large values of s, we can approximate this to only first two terms. Let it be 1. Let it be 1. Let us take one more system, g of s, that is equal, that has repeated poles at sigma a. How many repeated poles? n minus m repeated poles it has. N minus m repeated poles at sigma A. If we expand this, in binomial expansion, you will get s power n minus m plus sigma A s power n minus m minus 1 plus etc. If we compare these two, the second term is equal to, here one more coefficient, that is n minus m. Here coefficient is n minus m sigma A s power n minus m minus 1. N minus m. So this is binomial expansion of this to the power n minus m. So if you compare these two, what you will get is n minus m multiplied by sigma A equal to sum of I equal to 1 to n poles minus sum of j equal to 1 to m, sum of zeros you will get. Therefore, sigma A equal to sum of real parts of sum of poles minus sum of zeros divided by n minus m. N minus m. But we know that the complex conjugate will be plus minus, 1 plus 1 minus. If you add, complex part will be getting cancelled. Therefore, instead of writing like this, we can write sum of I equal to 1 to n, real part of poles minus sum of real parts of zeros, divided by n minus m. Therefore, sigma A equal to the point at which the asymptotes are meeting is sigma A. How we are comparing these two? Here, how many repeated poles? N minus m repeated poles at sigma A. No zeros. N minus m root locus branches will end at infinity, the second case. So, in the first case, m root locus branches already end at 0. The remaining n minus m are there. That's why these two are identical. That's why we can compare these two. If we compare these two, we are getting this relation. N minus m sigma A equal to sum of poles minus sum of zeros. Therefore, sigma A equal to sum of real parts of poles minus sum of real parts of zeros divided by n minus m. So now, by how many rules we have seen? 5 rules. Let us draw root locus for this.